Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the very good stuff. This is the AAS Journal Author Series. And I'm super happy to have Anne Limbach with us today. Hey, Anne.
Hi, how are you?
I am doing what we are October 27th, 2021, as we're doing this recording. And we are a few days from the American holiday known as Halloween. So are you getting ready for Halloween?
Yes. I'm quite excited, especially last year it was a little bit quiet. So hopefully there'll be a lot more excitement this year. But certainly a lot of decorations in our neighborhood.
Oh, cool. So where is, what's your geolocation? Where are you at?
So I'm in College Station, Texas. So if you imagine Houston, Austin, and Dallas, it's sort of at the center of those three. Yes.
Mm-hmm. Cool. Very good. Yeah, Halloween in my neighborhood, which is Phoenix, Arizona. Last year was completely nil. I put a bowl out given the circumstances and hardly got any takers at all. So I had these mounds of things left over last year. But this year I'm hoping it'll be a little bit better. So I kind of did my usual and got 80 little bags together, and we'll see what kind of take we get this year. So it'll be exciting.
Yeah.
Let's see, that is a pretty awesome picture over your right shoulder. If I got the parity right there in the camera. What is that? Is that the Trepid?
I think it's actually Orion.
Orion, okay.
Yeah.
Very nice, very nice. Did you take that picture?
No. You know, it's something, my husband's actually an amateur astronomer.
And that is awesome. Okay.
Cool. So he's had it forever, and so it's a great background. So yeah.
Does he get Sky and Telescope?
He used to a long time ago, but these days he has less time for such things. So
okay. Yeah. Well, if he wants, we do a Sky and Telescope series. So we get Sky and Telescope authors to talk about their astrophotography, their telescope making, all this kind of stuff. So maybe give him a hint if he doesn't necessarily want to get the magazine right now. He can always just watch one of the videos on Sky and Telescope. Folks.
I'll tell him about that. He'll be excited.
Cool. Yes. Very cool. Awesome. Anne, what do you like to do for research?
So a couple different things, actually. So I actually started in instrumentation. Yeah, I've done exoplanet instrumentation for a decade. But more recently, I've sort of been shifting to exomoons. So I'm very interested in how we might be able to find them in the near future, hopefully. So I've been thinking about that a lot, trying to come up with some fun ideas on how that might happen.
That would be awesome. Well, I hope, since you've done instrumentation, I hope you detect the first one. And that is going to bring us to this very lovely APJ letter on the detection of exomoons transiting isolated planetary mass objects. And Anne, take us away.
All right, thank you. Yeah, so we recently published this paper on detecting exomoons around isolated planetary mass objects. I worked with quite a few amazing people on this. So Joanna Voss, Josh Wynn, Renee Heller, Jeffrey Mason, then Adam Schneider and Faye Da all helped me put this paper together. So thank you. Okay, so to get started, I just want to start with the question. Okay, so why are we looking for exomoons? And so to date, we've found over 4,000 confirmed exoplanets, but we have yet to find an exomoon. But despite the fact that we haven't found any, there's good reason to believe they're out there. So the gas giants in our solar system, they all have exomoons. So Jupiter, imagine, the 4 Galilean moons. So you've got Europa, Io, Ganymede, and Callisto. These are all relatively large moons orbiting Jupiter. The other gas giants have these as well. And so based on our solar system, the gas giants in our solar system, it would appear that moons around gas giant planets might be common. And so certainly there's good motivation to go look for these objects. And in this paper, we're discussing detecting them sort of around these planets that don't have stars. So
Okay.
To introduce what these objects are, let's skip down to figure 7, and then we'll come back and do this in a more linear fashion. But
so figure 7, there we go. Blow that up for 1080p, and there we go.
Okay, so what we have here is all the, or most of the known directly imaged exoplanets. So these are exoplanets that are orbiting stars nearby. And they're young and bright and sufficiently well separated from their star that we're able to use high contrast imaging to take pictures of these planets. So those are the ones marked with a star on this figure.
Yep.
And you can see sort of Beta Pic, the HR8 799 planets, all the way down to a few fainter things. So like the white dwarf planet 0806b. Which is bigger and therefore fainter. And so these are all these directly imaged planets are sort of 1 to 13 Jupiter masses, and that 13 Jupiter mass is an important cutoff. So above that limit, we call it a brown dwarf because it's able to fuse deuterium, and below that, we would call these companions of stars exoplanets. So there's also a population of these objects sort of in this 1 to 13 Jupiter mass range that we can image that aren't orbiting stars. And so we are calling those isolated planetary mass objects, or IPMOs. They're typically young. The young is important because they need to be young to be bright. They cool over time since they're not fusing anything. And so most of the IPMOs that we know of and that we are able to detect are nearby, and they're young. So you can sort of see on this axis over here, you're looking at objects that are typically younger than 300 mega years, and often, you know, only 10 to 100.
Right, on the brighter side. Yep. Okay, I'm with you.
The key takeaway here is that these IPMOs and this directly imaged exoplanet population, they overlap and they're very similar. So the IPMOs, they have the same mass and age and spectral energy distribution as these directly imaged exoplanets. And so these two populations of objects, because they are similar, often sort of serve as an analog for each other. And more specifically, it seems reasonable to think that the companions, the exomoons that form around directly imaged exoplanets might be somewhat similar to the exomoons we could find around IPMOs. So if we're able to look for exomoons around IPMOs, that could tell us something about the exoplanets around, or the exomoons, sorry, I misspoke there, the exomoons around directly imaged planets, and generally the exomoon population in general.
Cool.
So a caveat to this, so these isolated planetary mass objects, which are sometimes called free-floating planets, we're not sure how they formed. So one scenario you can imagine is that they formed in a circumstellar disk around a star, and then through some process were ejected into space, and then became free-floating planets, or IPMOs. Another possible formation mechanism is that they form sort of at the low end of the normal star forming process. So you can imagine these IPMOs may have, there might have been a gravitational collapse just as stars form, but there wasn't much mass there. And so rather than getting a star, you just got a planetary mass object. And in general, we don't know what fraction of these objects formed via which mechanism. But it seems logical that, you know, if they formed around a star and then were ejected, it seems reasonable to call their companions exomoons. However, one might argue if they formed via the star forming process, then what we should call their companions, an exomoon or something else, is very debatable. So we call them exomoons in this paper, but we acknowledge the fact that it's not necessarily clear that they should in all cases be called that. But I think they do represent sort of analogs of exomoons whether or not they should be called exomoons. Okay, so in this paper, we're discussing the detectability of exomoons around IPMOs, and specifically, we're looking at the transit method.
Okay.
And we're going to start by talking about how easy we think these objects might be to detect. So how often they should be transiting, how long they should be transiting, what their transit probabilities are, and if we can find them.
Cool.
So to do that, let's go up to figure 2.
Let's pop up to figure 2. Okay. And we're at 4, 3, 2. Okay. Blow that up a little bit. All right.
All right. So.
Okay. Okay.
Sort of where we started was that so Jupiter and all the gas giants in our solar system have a lot of moons, and several of these moons are quite large. So let's take, for instance, Io and Europa. So if you were to observe a Jupiter-like planet with the Galilean-like moons outside our solar system, and let's say you observed 10 of these Jupiter-like objects at some random orientation, some random viewing angle, then we would expect, after observation of just 10 of those Jupiter-like objects, we would find one system that was oriented such that transits occurred.
Okay.
So the transit probability of the Galilean moons are quite high. Therefore, you don't need to observe many of these gas giant planets to expect detection of a moon system similar to the Galilean moons or the other moons in our solar system.
Okay.
So what this plot is saying here on the left is that sort of after observation of about 10 Jupiter-like planets, you could expect to detect you would have a 50 to sort of 60% chance of detecting those Io and Europa-like moons. On the other hand, if you wanted to find something like Mercury, you would need to observe 100 sun-like stars to be able to have a sufficient transit probability to detect that sort of planet. And for Jupiter, you need to observe even more objects. So it's about 1,000 sun-like stars before you can detect a Jupiter analog. So in general, there's reason to believe that moons have a much higher transit probability than sort of the planets that we see in our solar system, and that are generally have a higher occurrence rate in other star systems. So not only are the transit probabilities of the moons in our solar system quite high, but they also have a reasonable transit depth. So if you can convince yourself that you can do sufficient photometric precision photometry on these objects to detect the transit depths are reasonably high. So for all of the gas giants in our solar system, they all have a moon with transit depths comparable to sort of Uranus and Neptune. And so these transit depths are sort of at this 0.1% level. And that's important because we've found in observing exoplanets transits that transits of this level are typically limited by photometric precision rather than systematics in the instrument. And so if you're able to achieve the photometric precision you need, sort of systematics on the instrumentation should not be an issue for detecting transiting exomoons.
Okay, I'm with you.
Okay. Yep. The other great thing about moons is they typically have very short orbital periods. So to detect planets similar to the planets in our solar system requires observations of hundreds or even thousands of days to detect, even one transit. Whereas to find the moons in our solar system, you need to only observe for a few days to find a transit. And so the survey timescales for finding these objects are much shorter. Okay. So in general, there's reason to believe there might be a high transit probability, reasonably large transit depths, and short orbital periods, which should also all help us detect these objects if we can get sufficient photometric precision. All right, so next let's go to figure 3.
Figure 3. Ooh. Okay.
All right, so we have several orders of magnitude of on the primary mass scale down here. We're going all the way from sort of Earth's up to the mass of the sun and a little bit higher. Okay, so we've looked at the transit probability of moons in our solar system compared to the planets in our solar system. But now we want to look at that more generally. So what we're doing is we're imagining a secondary that orbits the primary at 3 Roche radii. And so we're going to use 3 Roche radii because that's a typical separation of moons, like the closest in moon around the gas giants in our solar system. But it's also sort of a typical separation we see for a hot Jupiter around a star. So that 3 Roche radii is, you sort of see there for the hot Jupiters. And you also see a lot of planets orbiting, the closest in planet orbiting at this distance in these compact planetary systems. So across the mass range, this is a reasonable value for the closest in planet or moon that we expect to find orbiting a primary. Okay, so we place a secondary in orbit around the primary at 3 Roche radii. And then we ask, what is the probability that that object will be transiting the primary given a random viewing angle? And so if you go down to sort of the rocky worlds, you see that transit probability is sort of in the 5 to 10% range or a little bit lower. And then as you go up and you start to get these sub-Neptunes, so if you go up to sort of the Neptune to Uranus mass range, you start to get these envelopes, and as the density decreases, the transit probability increases. And so you're more likely to be able to detect moons around planets with volatile envelopes. And you sort of hit a peak in that transit probability at sort of a Saturn mass object, where your moons have a 15 to 20% transit probability. Yep. And then after that, the density of these planets starts increasing and the transit probability begins to go down into the brown dwarf range. Yes. Until you hit a minimum right before fusion kicks in. And so at that point, you have these very extremely high density primaries. And so the transit probability of even the closest in secondary is quite low. And so, but then once fusion ignites and you get into the stellar regime, the density goes down and the transit probability goes back up. And by the time you get to sort of a solar mass star, the transit probabilities are comparable to what we see with the gas giants. Yep. However, the catch here is that we actually don't see that many secondaries, exoplanets orbiting stars at these close-in distances. So the occurrence rate of hot Jupiters is relatively low. There's a hot Neptune desert, so we don't see many hot Neptunes there at all. And so even though the occurrence rate of these, so even though the transit probability of these close-in exoplanets around sun-like stars is reasonably high, there's just not that many there to detect. And so as a result, you need to observe quite a few stars to expect a detection of a significant number of transits because the occurrence rate of close-in objects is relatively low. And then sort of in this, bottom of the brown dwarf, M dwarf range, it might be that the occurrence rate is higher of these close-in objects. We've sort of started to see that, but the transit probability is low for these high density objects. So that sort of implies that for low density gas giants, sort of in this Saturn to super Jupiter mass range, there might be a sweet spot where we both see a high transit probability for close-in secondaries. And if the solar system moons are representative of objects that we will find here, then we also expect occurrence rates to be high. So it may be sort of the spot where we don't need to observe many of these objects to start finding transits.
Cool. Okay, I'm with you.
Okay. So next up is figure 5.
Let's go to figure 5. Ooh, okay.
Okay. So hopefully sort of at this point, I've convinced you that we have a good chance of possibly detecting a transit around of an exomoon around these IPMOs after observation of sort of just a handful of these objects. So the next question is how long do we need to observe them? So typical IPMOs are sort of 5 to 10 Jupiter masses. Most of the ones we know are sort of in that range. And so for that massive object, we expect orbital periods for these closest in moons of about of a few days. And most of these transits are going to last a few hours. And so after observation of just a few days of an IPMO, if there is a transiting moon system and you have sufficient photometric precision, you should expect detection.
Cool. Cool.
I actually think that's it for this plot, but I actually want to go back really quick to figure 4. If we could.
Ooh, got a little carried away there. Okay. Let's try that.
So,
okay.
So on figure 3, we were talking about the sort of transit probability for an object fixed at 3 Roche radii. Right. But instead, if we place the secondary companion in the habitable zone, which here we're defining as the location where the secondary receives the same bolometric flux as Earth.
Okay.
Okay, so just for this plot, that's the assumption.
Okay.
So if we place an object in that location around our primary, we can ask what the transit probability is of that object. Okay, so for hot stars that are very massive like the sun, you need to be quite far away from that star to be in the habitable zone, and that means the transit probability is lower. Right. And so then as you go to less massive stars, the habitable zone moves closer to the star and the transit probability goes up. It sort of plateaus around 2% for M dwarfs.
Yes.
Yeah. And then below that mass range, there's no longer fusion, and so your primaries cool over time. Yeah. And the habitable zone moves closer and closer to that object as it cools. But you can calculate where the habitable zone is at any given time. And typically, because these objects are cooler than stars, the habitable zone is quite close. And that means that the transit probability is quite high. And so specifically for most of the IPMOs that we know about, they are very young. They're sort of, 1,000, maybe 1,500 Kelvin. And the objects that are typically orbiting close in that we're likely to find lie in this habitable zone around these IPMOs. Okay. So of course, this habitable zone isn't going to last very long, but when we find these sort of newly born exomoons around these IPMOs, they're very likely to currently exist in their habitable zone of their IPMO. And so that's very interesting because it gives us a chance to see sort of terrestrial worlds in their infancy, if you will, things that may be akin to primordial Earth. And so even though they may not stay in this habitable zone forever, they are unique environments for probing conditions similar to what we think early Earth might have been like. And they're particularly accessible in the sense that they, unlike habitable zone planets around stars, they transit quite often, and their primary typically has a very small radius because these are planetary mass objects, which means the fraction of your habitable zone planet is relatively large compared to the host. And these high transit probabilities make it easier to probe the characteristics of these habitable worlds that may exist here.
Nice.
Okay. All right. So next is figure 6.
Figure 6. Ooh, there we go. Okay.
All right.
Let's start on the left here.
Okay. All right. So at this point, hopefully I've convinced you that with a few days of observation of about 10 IPMOs, we might expect detection of an exomoon. You have convinced me. Okay. Excellent. Good. So the next question is, if we stare at these IPMOs, will we have sufficient photometric precision to detect the sized moons that we expect to exist there? So first, let's ask this question for these directly imaged exoplanets. So at the beginning, we were talking about these exoplanets that are around these stars that are sufficiently separated to allow for high contrast imaging of them. So for that case, you're using these 8-meter ground based facilities and high contrast imaging to image these exoplanets. And the question here is, can you monitor the photometry of those exoplanets sufficiently well to detect an exomoon? So the issue here is that high contrast imaging is very difficult. And so you get a lot of starlight overlapping onto the planet. And this essentially leads to noise in your photometry. And because of that, our photometric precision on directly imaged exoplanets is sort of currently limited to about 5 to 10% precision, which means, and in the best case, sort of we're starting to maybe get down into the 1 to 2% regime. But even with that level of precision, we're sort of stuck at being able to only detect Neptune-sized moons around directly imaged exoplanets. And we really don't expect there to be that many moons that are that large. So currently, exomoon detection, transiting exomoons around directly imaged exoplanets is likely to not be that successful, just because we expect the occurrence rate of these extremely large moons to be very low. Okay. So then if you ask the same question for these exomoons around IPMOs, you can first look at what we can do from the ground. So from the ground, with an 8-meter telescope in the K-band, you can get sufficient photometric precision to detect Earth-sized objects. So, and that's pretty good. So you sort of, for these large IPMOs that are sort of 10 to 13 Jupiter masses, if you sort of scale up Titan, let's say, so Saturn's moon Titan, if you were to scale it up to a 10 to 13 Jupiter mass object, Titan would be the size of Earth. And so you expect some of these large IPMOs to have Earth mass moons. And furthermore, because these IPMOs are young, these Earth mass moons are still likely to have an envelope. So when Earth first formed, it had hydrogen helium envelope. It lost it very early on, but it's likely that most of these IPMOs are young enough, their moons might still have those. And so that really increases the transit depth and makes these objects much easier to detect.
Okay.
So it's plausible from the ground that you could do this with an 8-meter telescope.
Okay, nice.
But where it really works the best is with JWST. So IPMOs are brightest in the near infrared, and which is where JWST operates. And so for JWST, you're able to get to sort of 100 to 200 parts per million photometric precision on most the known IPMOs. So there's about 57 nearby well-characterized IPMOs, and for all of those objects, you're able to get to this sort of 100 to 200 part per million precision.
Cool.
And so with that precision, you're able to detect moons as small as the moons that we see in our solar system. And so that's really exciting. We expect there to be a lot of these, especially since the IPMOs are going to be much more massive than the gas giants in our solar system. And so this size of moon should be extremely common. JWST, if there's a transiting moon in these systems, is very likely to detect them.
Okay, nice.
We can sort of shift over to the right here now.
Okay. Wideband. Okay.
Yes. So we're at 4.5 microns on the bottom x-axis. All right. This is a plot of all the known IPMOs, and so IPMOs, just like directly imaged exoplanets, can be classified in the sort of the similar way that we would classify stars, in that we can assign them an L dwarf, a T dwarf, or a Y dwarf classification. And this is true too for directly imaged exoplanets. For example, one of the objects that we talk about later is an L7 dwarf, and 2 of the HR8799 exoplanets are also L7 dwarfs. Just for comparison, that's sort of where we're at here. For these 57 known IPMOs, you can sort of detect with a 5 sigma confidence with JWST moons ranging in size between Triton and Mars, and for a few cases up to sort of an Earth-sized object. But in general, we expect moons around these IPMOs to form that are about the size of Mars. So most IPMOs are going to have sort of Titan to Mars sized moons, if not bigger. And so what this plot is implying is that given the size of moons we expect to be forming around these IPMOs, JWST should have sufficient sensitivity to detect them if they're transiting.
Okay.
Nice. And that is exciting. Okay, so there's one complicating factor, and so we will discuss that next. So let's go to figure 9.
Figure 9. Okay, looks like some light curves. Okay.
All right. So the thing that makes detecting transits of IPMOs difficult is that the hosts have clouds and are rotating. And so you get these variability, variable rotation curves as these cloud structures come and go. And that leads to first order a sinusoidal light curve. But there's also a lot of sort of random variability on top of this. And depending on your IPMO, that level of variability can make exomoon detection very difficult. One of the things we tried to do in this paper was sort of look through known light curves of IPMOs and sort of get a feel for how much this variability would be problematic for detecting exomoon transits. And although we weren't looking, we came across one light curve that happened to have a little bit of an excursion in it. So we decided to use this one as an example.
Okay.
So, and this is the light curve of 2-mass 1119 AB, and it is actually a binary. So there are two roughly 4 Jupiter mass free floating planets, or IPMOs, in orbit around each other. They're separated by about 4 AU.
Okay.
And they're on about a 90-year orbit. Okay, and so Spitzer did not resolve these. They have been resolved in other observations. That's why we know there's 2 there. But this light curve is unresolved, so it's of both IPMOs.
Okay.
And what we see here is a sinusoidal rotation of a few hours, and that is presumably from one of the 2 IPMOs. But we also see sort of an event at the 8-hour mark that lies sort of outside the normal range of variability for this object. So you can see on the left, you're doing the observations in 2 bands here. So first you do 10 hours of observations in the 3.6 micron band of Spitzer, and then the second observation is another 10 hours in the 4.5 micron band. So you can see that the amplitude of the rotation variability is a little bit higher in that 4.5 micron band. And that's normal to see a little bit of different amplitude in those 2 bands. But so in the 3.5 or in the 3.6 micron light curve, we attempt to fit what appears to be this possible event at the 8-hour mark. And so we do that a couple different ways. We do it with a sign plus box model, and then we do it with a Gaussian process plus box model. And in both cases, we find that the model with an event versus no event, so this box at the 8-hour mark, is marginally favored or favored in the case of the sign. And so it suggests that perhaps this event is, so the question is, what caused this event? And so there's sort of 2 possible answers there. One is that we caught this object on a particularly stormy day, and there was sort of a large event on the surface of the IPMO that caused a dip in the flux, and that's what we're seeing here. The other option, of course, is that there was an exomoon transit during this observation that led to this event. And so there's clearly not enough data here to say one way or the other conclusively. But the light curve does do an excellent job of demonstrating what an exomoon transit might look like, and how variability will affect our ability to detect these objects. And so I think one of the biggest takeaways here is that moving forward, if we hope to successfully detect these objects, we need to come up with ways to mitigate variability. And so one of those ways is with JWST. So most of the observations that will be done of IPMOs with JWST will be done in a spectral observational mode. So you'll get these spectrally resolved time domain light curves, and variability is very chromatic relative to your transit. And so the chromaticity of the variability due to the rotation of the planet will look very different than your achromatic transit event. And so that spectral information from JWST will hopefully allow us to differentiate between these transit events and rotational variability.
Cool.
Yeah.
Very cool.
All right. So I think that is really the main main part of the paper. I might stop there.
Cool. All right. Let's slide up to the top. And Marianne, thank you so much for walking us through your very lovely letter.
I was happy to do so. It was fun.
You touched a little bit there about it at the end. So let's go there for a little bit toward the future. So number one, I suppose I should ask if you got your JWST proposal in, or you will be putting in some. You know, are there other observational campaigns coming up? How about Vera Rubin? Can that do anything for this? Are there theoretical calculations that could be done on, you know, cloud models around these spectral types to maybe help distinguish a little bit between what might be a cloud or a storm versus a true exomoon? So just kind of give it a future look on where do you think we go over the next, let's say, couple of years?
Sure. Yeah. So for the event that we found in the 2-mass 1119 light curve, we are hoping to follow that event up. Fortunately, the event that we saw there was fairly large, so it's a 0.6% transit depth if it's a moon. And from the ground, you can resolve the 2 IPMOs, right? So if you can monitor them from the ground, that gives you, and separate out your 2 different light curves, that gives you a 1.2% transit depth, and that's doable from the ground. So we're hoping to follow up this event that we saw from the ground, and see if we're able to detect more events that might indicate this could be an exomoon, with follow-up ground observations. And we're also hoping to apply for JWST time in the next round, because that will address our ability to sort of differentiate between the variability and possible transit events in this object.
Yeah, so it's a binary. So I guess the exomoon would have to be pretty close to one of the objects in order, and even then one might worry about stability of.
Yeah, so we looked at the stability. We looked at the stability a little bit, and so the IPMOs are fairly well separated. They're 4 AU apart.
Okay.
So we really don't think that stability is a problematic in the system. Mm-hmm. And certainly if you have a transiting moon, it's going to be extremely close to the IPMO most likely. So
the binary doesn't exist. It's in the gravitational field of 1. So okay.
Right. Yeah. So I think we're not too concerned about stability.
Okay. Awesome.
Yeah. So certainly follow-up observations of this specific object, both from the ground and hopefully in the future with JWST, will be possible. More generally, I do think that there are ways to survey for these objects, and we're working on that. We hope to have a paper out on that soon.
Cool. Look forward to seeing that paper. That'll be awesome.
Yeah. So more to come on that in the near future.
Cool. Very cool. Marianne, I want to thank you so much for taking the time and sharing your article with us.
Yeah, thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.